In the last video, we just finished the chapter 1 in the BSL. We defined the viscosity and the mechanism of the momentum transport. The mechanism of the momentum transport is happening by two mechanisms. We call this first one is the molecular, and the second one is the convective. So now I just wanna review where actually we are so far. After this review, I'm just gonna jump in the chapter 3 and to start the problem solution. Okay, now what we get from the chapter 1, we just uh, define this relation. We call this actually molecular stress tensor. Here, if I go this first R relation we found here, in here call actually this the stress tensor. Why we call this the stress tensor? This is because this has the nine elements. This term is just the definition of the pressure forces acting on the fluid. Because of the pressure, we said the pressure always acts on the perpendicular the surface. That's why in the three direction the pressure is effective. That term is the viscous forces, stress forces acting on the fluid. This has also 9 elements. So we just summarize, the book is summarized this 9 element in this table 1.21 is give the direction of the normal to the shaded phases, and is give the vector forces for all the direction xyz, and in the xyz we have 3 elements. This 3 element also inside of each has 3 individual elements, and total we have 9 elements. That's why we call this the stress tensor. Okay, now we obtain the another relation. We call this just that one, this topic of the generalization of the Newton's law of viscosity, and this relation here actually give the Newton's law of viscosity for the viscous forces acting on the fluids. This is the open form. We also obtain in here, this is the closed form here. This is the closed form of the Newton's law of viscosity here. And we know all this, the mu is the viscosity and v is the velocity vector, and mu and k another type of viscosity, and so on. We define here, actually if we define again, that one is the unit tensor, has this component, and is the velocity gradient here, and this transpose of the velocity gradient tensor, and this divergence of the velocity, so on. If you continue in this just go final part here in chapter 1, you just to find here convective momentum transport, second type of transport. The first one was the molecular transport, and second one is the convective transport. The convective transport is given by this formula you see here. Then we can define for the xyz direction what are the convective the momentum transport, This is the in the x direction has 3 elements. This is the y direction 3 elements. This is the z direction has 3 elements. That's why we call this tensor again, because of the 9 elements. And finally, we can write our uh, total uh, combined momentum flux by this term. The first term is the molecular, the second term is the convective. We divided convective, molecular is the two piece of force. The first one is the because of the pressure, second is the viscous force, and this is our final relation, just representing the combined uh, flux from combined momentum transport. Okay, this is the actually, if you go and check all this relation in chapter 1, you can find there. Now what we did actually we got before, we just got the definition of the material derivative. In here again, just want to go over again here what was material derivative. This is the any intensive variable of the system inside of the control system control volume, and this is the also we call the substantial derivative. We obtain this relation here. This is important relation, just keep in mind. And then actually then what we get from here, we obtain that one. Before here, then we obtain here the Reynolds transport theorem. In here, this f is the just showing any function inside of your control system. This function can be the extensive property of your system, like mass. It depend on your system size, like that. And this continues because the derivative of this function is available each point and there is no discontinuity. Then we have this relation again. This is the intensive variable of your system, like rho density, and we obtain Reynolds transport theorem. By using this then Reynolds transport theorem, what we get actually, we get this important result here, the continuity equations by the substantial form. This is actually open form of that one. Open form of that one is d rho over dt substantial derivative. D is equal partial derivative of rho respect to t plus is going to be v velocity gradient of the rho. So this is the open form of that. If I write this here and I put also exchange by this, plus going to come here, rho over velocity is going to be equal to 0, and this term we can write here divergence of the rho v, because the divergence of the any two vector, let's say v w, two things, not the vector, two things, rho, in here we have rho and the v vector is going to be like this, v velocity gradient of the rho plus rho divergence of v. So that's why if we write this and here and we take this the right side, and it's going to be minus, and we can obtain that result for the continuity equation. Okay, so continue for the next part. In the next part, we got that another important result again here for the linear conservation of the linear momentum. We define here the T is the tensor different than the book actually. Okay, then what we have here again in this form, we have the V dt should be equal to in here this is going to be equal partial derivative, then we should get we have like rho here, this showed in this form. Density is the constant. Density is the constant. Let me show in this another way. Another way actually. Okay. Actually, where this substantial derivatives come from? Actually, we have, let's say we have partial derivative rho v plus rho vv. This term you remember from the chapter 1 is the convective momentum transport. We can write this by this form. If the rho is the constant, I can take the rho out, then v over t, and I can write that one is the open form like this: v dot product gradient of v plus of v, and this is the gradient of the v. If the rho is constant, then from the continuity equation, this term is going to be 0. Cancel that term. Finally, we got that one here. So since this rho is constant, we can take this out here anyway here. Then this is going to be definition of the rho dv over dt. This material, there is substantial derivative, so this comes from here actually. So this linear conservation of linear momentum, the right side here, in here you see this term is stress tensor, is include the two force because of the pressure and the viscous forces, and it's come from the body force like because of gravity, and we put the convective momentum transport inside of this term by combining these things here, these operations. Okay, now if we want to continue here, let's continue here. Then what we get from here, you see, this stress tensor can be defined by this S minus B, also can be defined by this formula. This formula comes from the BSL, from the first chapter. Then we insert this in here instead of stress tensor. Then finally we obtain this form here. So we should remember this formula again. So now I just want to jump in the chapter 3. In the chapter 3, we just gonna start the problem solution, but before the problem solution, just remember the equation of continuity is similar to what we draw before. We obtain that equation. This is the closed form, this is the open form of this continuity equation. the physical meaning of the rate of the increase of the mass per unit volume. The right side, net rate of the mass addition per unit volume by convection. For we know from here this term is the divergence of rho v, sometimes written d rho v or so on. But another important uh, result is uh, we get the result is the incompressible fluid. When rho is constant, we obtain that one, that divergence of the v's give the result of 0. Okay, and the equation of the motion here, you see from here, then what did we get? We got this formula for the equation of the motion. This term is include the molecular and the convective transport of the motion, and we can write that one is the closed form here for the extensive can extend this term by that one. So rate of increase of the momentum per unit volume, the left side. This is the rate of momentum addition by the convection per unit volume. And this is these two terms represent the rate of momentum addition by molecular transport. We know this from the chapter 1. Then external force on the fluid per unit volume like gravity. So this is the closed form, all this is the open form of this all this formula. So far we obtain all these results. Also this is the open form, and in here we have here, let's say this is the closed form, substantial form in the same form of the same equation actually. So if you go from chapter chapter 3, now in the section 3.6, use of the equation of the change to solve the flow problems. Now it's time to apply all this derive equation, the solution of the problem. So what we draw actually, the first we are gonna, for the problem solution, the first step we are gonna utilize these continuity equations. In the second step we are gonna use the linear momentum of momentum equation, conservation of linear momentum. And the other equation, we are going to use the Newton's laws of viscosity to calculate the viscous forces, and we are going to use these uh, formulas. Then we are going to use the equation of the state to define the pressure, and we are going to use the equation of the viscosities to define the mu and the k's here. Okay. Uh, as a last part, I just wanna mention before the problem solution. Okay, the equation of the motion, we obtain that result, that one. When the application of this equation of motion in the specific case, let's consider Newtonian fluids. For the Newtonian fluids, actually, Newton's law of viscosity, we have that relation. As we know, for the incompressible fluids, divergence of v is gonna be equal to 0. That's why the second term in here, in this Newton's laws of viscosity here, that term is going to be 0 because of this term is going to be 0. So we just left that first term here, and we can write this here in this form. D here is deformation rate tensor. It is the same, equal that one. Now, but for the incompressible Newtonian fluid of the constant mu, if the mu is constant, then we obtain from here that formula, and because this is 0, then we just left that first term here, and we got that one. The del operator here, second order del operator. Then Now we can write this here by this form. Um, just taking this writing in the instead of this term is the viscous forces acting on the fluid. For the Newtonian fluid, we can write that one, that final relation. We call this equation Navier-Stokes equation applying for the Newtonian fluid. So we could just continue our discussion about the problem solutions in uh, chapter 3. Okay, the example, steady flow in a long circular tube. We know in the chapter 2, it gives some this example here actually. Okay, think about any flow through the circular tube. We have some circular tube. We consider this is the steady state, and this is the problem is giving. The laminar flow is the fluid of the constant density and the constant viscosity, and the vertical tube like this. It has some the length of L here. Our tube length here is given as a L. Then the radius is here the R. The liquid flows from this direction, from the downward, under the influence of the pressure difference and the gravity. So the pressure is affecting on the fluid and also gravity. The coordinate system is the in here cylindrical coordinate systems. Then we specify that the tube length is very large, the L is very large with respect to the tube radius to R. Then so that the end effect will be unimportant through the most of the tube. Okay. Now, for the problem solution, a problem is giving some very important knowledge, so you can solve the problem based on this knowledge. So the problem is postulate that from this the fluid is flowing this direction. Only we have the velocity element of Vz is uh, depend on the R. So your velocity in here you see from here laminar velocity distribution, just velocity is changing through the R. So Vr is 0 and V theta is 0 for this problem. So the pressure only is the function of Z, as the problem gives. Another important components here, viscous forces basically for the Z direction, viscous forces perpendicular to R, and the viscous forces by the R direction perpendicular to Z, these forces equal to that relation. So, okay, this is our problem. Now we are gonna derive uh, our equations and solve this equation to get the result to find the velocity distribution inside of our system. But before moving that part and moving the solution, I just want to introduce the use of the appendix in these books. If you go to appendix B, you see here Newton's law of viscosity is the closed form, and all the coordinate system xyz, a rectangular coordinate, the open form you can obtain here. Okay, now for the cylindrical coordinates here, for the spherical coordinates, that one. For this problem, we are going to just use these cylindrical coordinates. So we have r, theta, z. So if we continue in the appendix B, we have the equation of the continuity, the closed form. And these are all the open forms for the Cartesian coordinates and cylindrical coordinates and spherical coordinates here. The equation of the motion in terms of the viscous forces, we know we obtain that one before, and this is the closed form, and this is the open form. This is in terms of the substantial derivative for the Cartesian coordinates and cylindrical coordinates and spherical coordinates, so on. And this is the equation of the motion for a Newtonian fluid with constant rho and mu. If the fluid is the Newtonian, if the rho and the mu is constant, we obtain this relation before, you know. And in the closed form, these are the open forms of Cartesian coordinates and cylindrical coordinates and spherical coordinates and so on. Now just move the problem solution here. Now we, we, we are in the problem solution. So the solution, we postulate that V only the is